Hi, welcome to online tutorial videos from JCBRO Labs. For more information and to download the source code of this video, you can visit us at www.jcbrolabs.org. We also provide online training on latest technologies like Matlab, LabVIEW, Embedded System, Python, C, and other programming languages. And we also do freelance-based projects on specific topics. Okay, so for more information and to contact us, you can visit our website, which is www.jcbrolabs.org. So in this video, we'll talk about the simulation of amplitude modulation using Python. And at starting, we will learn some of the basics of the amplitude modulation, that means the mathematics behind it. And then we will move forward for writing the Python program for the same. Okay, so let's start it. Okay, so when we talk about a modulation, so first the modulation thing is in which some parameter of a carrier wave varies in accordance with the message signal. That is the definition of the any modulation. So in particular modulation, there are two things, like first is there is some carrier wave, or we say it as a carrier signal, and another one is the MT, which is denoted as the message signal. Okay, so as we said, in modulation, one of the property of the carrier signal varies in respect to this message signal. So when we're talking about the AM or the AMFC, amplitude modulation full carrier, so in this AM, the amplitude of the carrier wave varies with respect to the message signal. Okay, so ultimately amplitude is varying, and all the information of the message signal is encoded in the form of the amplitude variations of the carrier signal. So now let's have a look like how this carrier signal is generated. So let's say we have a carrier signal that is represented by ST, and this is the carrier wave. So carrier wave generally is a high frequency sinusoidal signal, like let's say given by AC cos omega ct. Okay, so this frequency of this carrier wave is higher, nearly 50 times or more than 10 times than that of the message signal. So we can write this S of t as like AC cos omega ct, right, plus if we have message signal, which is like MT into cos omega ct. Okay, so if we take the AC cos omega ct outside of this complete expression, it will become 1 plus Ka, which is noted as, we'll just give it. So this Ka is its value is 1 by AC, and this Ka is defined as the amplitude sensitivity. So amplitude sensitivity of the signal. So this is the complete expression of our AM wave, right, where AC is the amplitude of carrier wave and K is the amplitude sensitivity. So there are certain conditions for which for this amplitude modulation, and those conditions are defined with respect to the modulation index. So there is a specific terms which is widely used in this AM modulation, and that is known as the modulation index. So, or it is also known as the depth of the modulation. That means which determine how much modulation has been done for the carrier wave or the message signal. Okay, so this modulation index we can represent it either MA or MI. So let's say MA, it is the maximum of the message signal that means maximum of the message signal MT max divided by maximum amplitude of carrier wave. That means in other term it can be written as mt max, m of t max, if we go through from our definition, divided by AC, or it can be written as Ka into mt max. That means massive signal amplitude. So this modulation index could be less than 1. So when it is less than 1, the modulation is known as the under modulation. Okay, so this is required, under modulation condition is required, only then entire information can be recovered back, and we will learn how what is the meaning of it through the simulation. And if this MA is greater than 1, that is known as the over modulation, and in this case information cannot be retrieved back. So this MA can be written as Ka into mt max. That means the maximum, the amplitude, it should be less than 1 always, and it should not be greater than at an instant of time. So these are the basics. Let's take an example which will be for which we will be doing a simulation. Okay, so let's say a single tone modulation. So in single tone modulation means a massive signal is nothing but a sinusoidal wave, right? So single tone modulation means our carrier wave is cos wave like AC cos omega ct, and our massive signal which was MT, that is AM sin omega MT. Okay, so let's put into a formula of S of t which we just discussed. So S of t will be simply, if we take AC outside, 1 plus Ka into AM times of sin omega mt into cos omega ct. So now this particular term is a modulation index, so we can write it like AC cos omega ct is C of t. So we can write it like C of t and then bracket 1 plus this is the modulation index MA into sin omega mt. Okay, so this is will be the expression for a single tone modulation, in which this is the single tone signal, that means contains only one frequency component. So we will be writing the Python code for this particular expression. Okay, where this MA, it should not be confused, it can be written as like AM by AC for a single tone case, because the maximum amplitude of this sine wave is AM and carrier wave amplitude is AC. So modulation index will be simply AM by AC. Okay, so while we will writing the code, please keep all this mathematics in mind, and then we'll move forward. Okay, so let's open Python, let's switch to Python, and let's write a code for this. So open Python. So as you know, we are using this Python distribution, Anaconda distribution of Python, and from this Anaconda we are using this Spider IDE because it is kind of similar to Matlab. So let's first import Matplotlib library, which will be useful to plot all the signals, and then we will be importing NumPy to create NumPy arrays, and then we'll be importing pi from math, as it will become handy while writing the code. From math import pi. Okay, so first we'll close all the figures which were opened up. So plt.close all. Okay, so now let's generate a carrier wave, or prior to it let's generate the time axis. So from our previous video, you may be familiar with, like, if we are generating a sine wave or cos wave, this time axis generation is critical, because only then we will be dealing time only, and sampling frequency information will be dealt in as well. So let's say am underscore python, am underscore python oblique new. Okay, so let's say we have a sampling frequency of 2000 hertz, so that nothing changes, so that all the frequencies of carrier message signal sampling theorem holds good for them. So let's create n equals to so let's create a time axis np dot range 0 comma, let's say for 2 second duration, and at a difference of 1 by fs. Okay, now generate carrier wave. So in generate carrier wave, first we need to define carrier frequency. Let's say carrier frequency we have 100 hertz, and let's say carrier amplitude AC it is 1, and then the carrier wave C equals to AC into np dot cos 2 into pi into fc into n. Okay, so it is a carrier wave. And let's generate a single tone signal, in our case a message signal. So let's say FM is 2 hertz and amplitude, let's say first make a 0.5. So it should be noticed that, like, message signal frequency should always must be less than frequency of the carrier wave, and the message signal will be let's make it simple, a into m into np dot sine 2 into pi into fm into n. Okay, so this is a message signal. Now let's generate amplitude modulated signal. Okay, so S equals to, it was C into T. So C into, because if we go to the formula CT1 plus MA, so it was, we can write it like MT divided by AC, okay, divided by amplitude sensitivity. This is simple, it will be 1 plus M divided by A of C, because that was the amplitude sensitivity, and that's it, I think. Yeah, that's it. CT, MA, MT, yes. So this is a signal. So let's plot it. We will be creating, okay, let's first create a normal plot, plt dot plot n comma s, and make a title to it. Let's say plt dot title under modulated, under modulation case, because in this case magnitude of the message is less than 0.5, and generally this under modulation wave is generated and is transmitted for carrying the signal. So let's make under modulation case, and plt dot x label as time in seconds, and then plt dot y label as amplitude. Okay, and then plt dot grade, make it true. Okay, so let's hope everything is fine. Let's run it. Okay, this Matplotlib. Yes, so this is a perfectly amplitude modulated sine. So amplitude modulated signal, right? or I hope you may be familiar with it. And let's make a frequency a little less so that we can have a look of inner portions which will be easy to understand. Yes, so this is a 50 Hertz carrier wave and this amplitude modulated wave. Okay, so let's consider the case of three different modulation, like full modulation and then over modulation and all those things. Okay, so let's create plt dot subplot, and it must be 3,1,1. okay, so let's see. Yes, so under modulation case magnitude. Now let's make over modulation, full modulation case. So full modulation. So in full modulation, our AM will be equals to the carrier wave, right? So right now AM was less than the carrier wave amplitude. So let's generate the message signal again, and then let's create the amplitude modulated signal again, and then make a plot of it. Okay, so now it will be in 2, and this will be a full modulation. Okay, and it will be simply yes. So let's run it. Yeah. So this is a full modulation. So the problem occurs at these crossovers. The information lost due to which signal is don't get, we may not be able to retrieve it back. So this was the case for full modulation. Let's make the over modulation case as well. So over modulation, and make it in a different color, let's say red. Okay, green. And for over modulation, all the things will be same. The only difference will be AM will be higher than that of the carrier wave. So our carrier wave is amplitude is 1. So let's say massive signal amplitude to 1.5. Okay, carrier wave amplitude is 1. So we are making this massive signal amplitude as 1.5, and everything remains same 3, and make it in red color. Okay, and let's run it. So this is the case of full modulation. Okay, so there must be some command plt dot layout tight layout, I think. Yes. Okay, so this particular command is used to make used to remove this overlapping of these accesses. Okay, so this is the final case under modulation, which is perfect amplitude modulated wave, full modulation, and then full modulation, and this is the over modulation case. Okay, let's change it, instead of full it is over modulation. Okay, so now you can understand the concept at this here. These two envelope, upper envelope and lower envelope, has been crossed into each other. So if we will be demodulating this particular signal, so at here there will be a discontinuity will appear in the message signal, or a distortion will appear in the message signal, due to which we may not be able to extract the message signal exactly. Okay, so this is the disadvantage of this over modulation case, and that is why it is recommended that modulation is always less than the amplitude of the message signal, or the maximum amplitude of the message signal, I should say, should always be less than that of the carrier. Only then we will get a perfect AM modulated wave. So I hope you enjoyed this video and you learned about amplitude modulation. So if you have any doubt or any query, you can contact us through our mail, or you can comment below this video. Okay, further, don't forget to subscribe us in order to help us to keep making these free videos, free educational videos. Okay, so that's it for this video. Thank you.